All right, so the question reads, the distance between the sun and the earth is 1.5 by 10 to the 11 meters. State this distance in gigameters. All right, so let's write down what we're given with a nice marker like this kind of. Number one, 1.5 by 10 to the 11 meters. And I want to cancel out meters and I want to be in gigameters. So this is just saying like how many meters in a gigameter. In 1 gigameter, there is 10 to the 9 meters. Okay, in other words, giga means 10 to the 9. This is just the same thing. 1 gigameter per 10 to the 9 meters. Now we just divide by this. I think that's effectively like canceling out, 9 of these zeros. So it should be 1.5 by 10 to the 2, or what's that, 150 gigameters. You could type that in your calculator and make sure that like, oh yeah, that's how we deal with exponents. We subtract these, right? 10 to the 9. For the benefit of everybody sort of following along at home, it's like, I don't want to break my calculator out. Let me just kind of show you that here on the screen. So we got 1.5 by 10 raised to the 11th. So that's that number, divided by, I always like to use grouping symbols, and to the 9th, 150. So 150 gigameters. There you go. The question continues, the distance from the center of the Earth to a satellite above the equator is 42.3 megameters. The radius of the Earth is 6,380 kilometers. A microwave signal is sent from a point on the Earth directly below the satellite. Calculate the time taken for the microwave signal to travel to the satellite and back. Okay, so I think we should draw that out to make it a bit more clear. So if here is the Earth right here, and they're telling us the distance from the center of the Earth to a satellite above the equator is, so that distance there, right, from the center of the Earth out to this satellite. A satellite is a bow tie, you guys. Just a bow tie with the little lines like this, right? Like a TIE fighter. And we got 42.3. Now mega is just 10 to the 6. It just means a million. So I'd rather kind of convert that. 42.3 mega meters. That's the distance, from this satellite to here. So like we'll call that S for displacement. And it says the radius of the Earth itself is 6,380. Now kilo is 10 to the 3. So by 10 to the 3. Let me make this a bit more clear. Let me draw that a bit more clear. (6,380 kilometers). And so I know that, the decimal is right here, and we like to put scientific notation. It would be like 6.38 by 10 to the 6, like those 3 orders of magnitude you could fold into here. If you type that in your calculator, it knows, okay, like this is just as correct. It's just moving the decimal point sort of where it belongs. But kilo means 10 to the 3, and this is a very convenient way to just sort of do conversions and do it efficiently. So remember, the satellite way out here was 42.3 megameters, and that was away from the center of the Earth here. A microwave signal is sent from a point on the Earth below the satellite. And so we want the time that it takes the microwave signal to go to the satellite and back. And so we really just want this distance here, right? So it's going to be this distance minus this distance. And then that would be the distance the satellite is above the Earth. The other thing we got to know here is that microwaves are light, and light travels at approximately this speed. This is the speed we should use when we calculate with light. The actual value is this, 299,792,458 meters per second, but it's so close to 300 million meters per second, we just kind of round it to that, and it's not, it's pretty close. All right, so in my calculator, I'm going to first calculate this distance, and then I have to realize that the light is going to travel at this speed, that distance, but it's got to travel that distance twice. So I should be able to calculate the time just by sort of using the equation that we've been introduced to, which is that speed, velocity, is distance over time. It's like in general, you know, speed, velocity is distance over time. Here, the thing that's traveling with the speed is light, so it's a really fast speed. All right, so you guys, if you've got a calculator, go ahead and take it out so you can kind of check my math here. If I make a mistake, call me out on it. All right, let's get rid of some of this. All right, so I'm going to start with the 42.3 times 10 to the 6. So there's my 42.3 megameters, 42 million. And I'm going to subtract away the radius of the Earth. And so minus, I use parentheses here. There's nowhere I can put this to make it clear, I guess. So I'm typing in this value right here. So 6380 times 10 to the third, right? And so take away the 6,380,000 meters of Earth radius, right? That's the distance in meters. Remember a meter stick from yesterday? That's how many of those to go from your feet down to the center of the Earth. It's always good to sort of think about that, right? Like, oh, 6 million meters, that's the radius of Earth. Cool. So we subtract that away to get the actual distance, you know, from the surface of the Earth to the satellite, right? Because they sort of gave us the data like that. And so that's the distance the light has to travel, but it's got to go that distance twice, right? It's got to go there and back. It says to the satellite and back. So the light is really traveling. Let's go ahead and double that. The light is traveling that many meters, right? We're in meters. We converted all these, you know, kilometers, megameters, converted them all. You can see that this question is designed to assess your knowledge of, did you memorize your metric prefixes? You know, giga means 10 to the 9. You know, mega means 10 to the 6. Kilo means 10 to the 3, right? We've seen a lot of them. So we're going to use this equation and we're going to solve for time. And so a little bit of algebraic manipulation, the old algebra switcheroo here, right? This v and this t can switch spots. Right? Multiply both sides by t, divide both sides by v. The time is distance divided by velocity. If you need to get to Miami 200 miles away in 1 hour, you just go 200 miles per hour, right? That was a fun weekend. I mean, no, don't do that, class. That's violating other. You can break the laws of man, but not these laws of physics, okay? That's something important to keep in mind. All right, so the distance here is going to be this number. Let me put it in. That's kind of tough. That's kind of tough on the eyes. 71,840,000 meters divided by the velocity, which is the speed of light. So that's, you know, this number, 3 by 10 to the 8. So the light has to go that distance, and then we can just solve for the time. So I'll put it in this column. 3 by 10 to the 8 meters per second. See how the meters cancel? We're in seconds of time, which is what we want to be in. And so everybody with a calculator out there knows that 71,840,000 divided by 3 by 10 to the 8, 300 million is 0.23946 repeating seconds. And so let's round that to 0.24 seconds. So about a quarter of a second to send a microwave signal to the satellite and back. Like, this is what's going on with your cell phones all the time, right? Communicating with satellites that are about that distance away. That's how it's like, you know, like if you maybe called somebody, but they're like standing in front of you, you can see them talking, but like you don't hear them. It takes a little bit of time for it to be relayed through satellite. Don't disconnect this from reality. It helps us sort of learn a little bit better. All right, so that's some metric stuff, conversions. The question goes on to read, the speed v of a sound wave through a gas of density rho and pressure p is given by that equation where c is a constant. We have to show that c has no unit. So this is a base units type thing. We got to know how to sort of measure all these quantities. This is a 3-mark question. Let's try to make short work of it. We know that velocity is measured in what units? Actually, let's do something else first. What can we do mathematically to this to kind of like make it a little bit easier on us? Anybody know? Get rid of the square root by squaring everything. Just square everything and makes it way easier to deal with, like b squared is equal to this. Okay, than to work underneath the radical, in my opinion. So the units on the left side, right, like we just rewrite this equation like this, same equation, okay? What are the units on the left side? Meters squared per second squared, right? Because velocity is in meters per second. So when we square it, we're also squaring the units. So we have to figure out we have to show that c is not going to have any units. Like these things are already going to give us meters squared per second squared. So c is just some dimensionless constant, all right? Those happen all the time. All right, so let's look at pressure and let's look at density. Pressure is force per area. You may recall we saw one example of pressure in some of our working last week, the evidence of which is in your journal that I grade before the end of class. So you may recall that we have a Newton of force per meter squared of area. Does anybody remember the derived unit that's equal to this? What's equal to a Newton per meter squared? You guys are so lucky you get this bonus review. 1 Pascal is 1 Newton per meter squared. Bonus, units along the way. Lucky. All right, remember that a Newton is a kilogram meter per second squared, and we still have these meters squared down there from area. So we saw this last week. We had to show that the base units of pressure were kilogram per meter per second squared, right? So in the numerator, from this pressure, we've got kilogram per meter per second squared, right? Those are the units of pressure. So these units here just come from pressure. These are the units of V squared, right? And so what do we got left? We got the units of density down here. Everybody remembers that density is mass over volume, right? How much matter we can cram into a given amount of space. So we got mass measured in kilograms and volume measured in cubic meters, right? Meters times meters times meters, length times width times height. So those are the base units of density. So we're plugging density into the denominator here, right? Kilograms per meter cubed. And now we can see that those kilograms cancel. And this meter cancels one of those. And we got meters squared per second squared. Nice, that's what we wanted. So we've shown that C, there is this, constant C up here, but it doesn't have any units, right? The units already work. You divide density into pressure, pressure divided by density, same thing as velocity squared, same units. The C is still here. So remember what we're doing is that these are quantities, right, that are related in an equation. We're just looking at the way that we measure those things, the units, right? The units have to work. This was the idea from last week, base units. So C is still in this equation, but it has no units, right? They told us, hey, show that C doesn't have any units. For this equation to be valid, the units on the left have to equal the units on the right. And they do. They do just from the units of these guys, right? Like the units of pressure gave us this, and the units of density gave us this. And when we combine it all, the kilograms cancel, one of the meters cancel, and we're left with meters squared per second squared, right? The left equals the right. We didn't have to do anything with C. C doesn't have any units, right? It doesn't contribute any units to this calculation. And we've shown that. Mass is measured in kilograms. The question goes on. Underline all the scalar quantities below. So remember vectors and scalars, right? And you had to sort of check boxes on a list or something like that. And so by now we've maybe introduced a number of these, but not all of them. So we just want to underline the scalars. Acceleration, that's a vector. Acceleration is a vector. Energy is a scalar. Momentum is a vector. Power is a scalar. Weight is a force. Forces are vectors. So vector, scalar, vector, scalar, vector. And we'd only underline these two. I always wonder, like, what if you circle it? Should I count that? Like, you knew the physics Like you knew to find one, but you didn't follow directions. Should I be harsh and like, mark against you for that? I don't know. I just kind of like, well, they knew the physics. Follow directions. All right. A boat travels across a river in which the water is moving at a speed of 1.8 meters per second. The velocity vectors for the boat and the river water are shown to scale in figure 1.1. In still water, the speed of the boat is 3 meters per second. The boat is directed at an angle of 60 degrees to the riverbank. And it says, on this figure, draw a vector triangle or a scale diagram to show the resultant velocity of the boat. Determine the magnitude of the resultant velocity of the boat. All right. You got a boat going like this, you got water going like that, and we have to draw a vector triangle or a scale diagram. Now they say that this is shown to scale here. All right, so I guess the length of this line corresponds to 3, and the length of this line corresponds to 1.8. If you had a ruler and a piece of paper in front of you, like with this question on it, you could kind of use that, and you could just use a scale drawing to solve it. Like if you draw vectors to scale, your scale drawing can actually solve this thing. But there's also a way to solve it maybe with a little bit of mathematics. Let's think through it like this. Does anybody recall the rule for how to add vectors? We've got the boat velocity, but we're going to add the water velocity to it. You can't avoid that if you're in a boat in water. Like the water velocity is going to affect the boat's motion. It's maybe because the boat captain wanted to cross this river this way and knew the water's pushing him this way, that he said, well, let's head off at a heading this way. That way the water will sort of push us back in a direction that just kind of takes us straight across. That's kind of what I suspect with this, just because the water's going this way and the heading is this way. So maybe this adds up to just straight ahead, but we don't know. They don't want the direction anyway. They just want the magnitude. All right, so the rule is you place the vectors head to tail. So this is, it's telling us it's pointing this way. They draw the arrows sort of in the middle of them, but like that's indicating that, okay, well, the head of this vector is right here, right? This vector is here and it's pointing that way. So there's the tail of it. There's the head of that vector. Now, if I was very careful and I like drew this, again, it's to scale, I could do the exact sort of distance and connect it and sort of see that way. And then when I draw this line that connects them, remember the resultant is connecting the head of the tail of the first vector to the head of the last, call it R for resultant. I could actually measure that with my ruler and say, well, if this many centimeters is 1.8 and this many centimeters is 3, to kind of use that proportion and that scale to just solve it with a ruler, with a scale diagram. So if this vector goes up and to the right, then that means it has a component that's going to the right and it has a component that's going up. This vector just goes completely to the left, all right? So what I've done with my initial boat velocity vector here is I've resolved it. We say resolving the vector is when you break a hypotenuse down into its x and y components, all right? So one of the ways to add vectors is to resolve the vector, because we can add, it's easy to add, like if I gave you a simple problem like there's a force of 10 newtons this way, and there's a force of 15 newtons this way in the tug of war. What is the net force? Even though we haven't really studied that, you probably know what the net force is because it's intuitive, right? So what's the net force here? Tug of war, 10 newtons of force this way, 15 newtons of force that way. What's the solution to that vector addition? 5 newtons right. The direction matters, right? So it's just like, oh, if they're in the sort of same plane, the same sort of axis, then it's easy. So if we know how much of this 3 meters per second is going this way, then we can just sort of add it to the 1.8 meters per second that's going against it. And then all we have left is this sort of vector here. So how do you resolve a vector? In other words, this vector right here is the 3 meters per second. It's a velocity of 3 meters per second. At 60 degrees, you could say above horizontal or relative to the positive x-axis. this side right here, that's pointing right. Like a vector that goes up and to the right has a component to the right. So that's adjacent to this angle. We could remind ourselves that the cosine of 60 degrees is equal to the adjacent side. You could call it like, I don't know, the horizontal component of this velocity over the hypotenuse, which I know is 3. And so I can readily calculate how much of this 3 meters per second is going to the right. But you do need some trigonometry. It's not, that straightforward. So you got to break out the calculator and sort of see that. The cosine of 60 degrees is a half, and half times 3 is 1.5. And so of this 3 meters per second, 1.5 is going that way, which means there's a net velocity this way, right, of 0.3 meters per second. When I add the rights to the lefts, I'm left with 0.3 meters per second left. Now I still have this up component. How much of that is up? That would be the sine of 60, right? Because that's opposite, would equal the vertical component of velocity. And so solving that for velocity, we realize that the sine of 60 is 0.866 times 3. And so I still have a 2.59 meter per second up velocity. Now you can use Pythagoras' theorem to solve for the magnitude of the results using these two right here. I'll leave that to do on your own. Check back later for the complete worked example on question 1 part E, and we'll see you next time.